Okay, in this video I'm going to look at one of the four primary components that are used in Rankine power cycles. And this is a turbine. Turbines come in all sorts of different forms. This is a hydraulic turbine that you would see, installed in a dam. It's going to generate electricity, and the water flowing through due to potential gravity change will drive this thing. But you can also have wind turbines, or the ones that most of the time we're talking about are going to be ones where we have some sort of high energy fluid flowing through and turning blades and producing power. Now, if we wanted to analyze these, we need to do these using the first law, second law, and so forth. Now, ideally, most of these things are going to be steady state, and frequently they only have one stream in and out. So for now, that's what I want to analyze. If they're well insulated, then I'm going to say that Q is 0. And although there's usually some sort of kinetic or potential energy change, those changes are usually small, and so we can neglect them. So the resulting balance, if I go through the first and second law, gives me that the specific work of a turbine is the inlet enthalpy minus the exit enthalpy, and the entropy generated is the exit minus the inlet entropy. Now if I take those two results and also combine this with turbine efficiencies, then I know that the actual work over the reversible work is going to be the turbine efficiency of a number less than 1. And that's HI minus HE, because the first law is true no matter whether it's reversible or not. I'm going to take the actual exit enthalpy in the first case and the ideal in the second case. I'm going to find out what's going on in the ideal by saying, well, if it's reversible, then S generated is 0, which means that SE and SI will be the same, or an isentropic process. So if we briefly look at a couple of quick examples, well-insulated turbine, I've got a flow rate given, temperature and pressure, and I have an exit pressure. And what I want to know is how much power this could produce if it were an ideal turbine. So I'm going to need some data. Now I got this data from a data source software, and so what I found is at 500 degrees C and 1.5 megapascals, the inlet enthalpy is 3473. And if I use this value of entropy 7.57 with the pressure of 1 megapascal, I get an enthalpy of 3336. Plugging those numbers in, I come up with roughly 3.4 megawatts of power ideally produced. Now, what if I wanted to look at this as for something that was not perfect, or inefficient, or not inefficient, but an irreversible turbine, one that's only 83% efficient? Well, I start by using that ideal number that I calculated and now combine it with the turbine efficiency. So I can use it either as specific work or power, whichever one is more convenient. And in this case, power is what I've calculated. So I'll use that, and I find out that actually it's only going to produce 2.8 megawatts of power. I can use this, although this problem statement didn't ask for it, but I can use this to calculate the actual ideal, or the actual exit enthalpy, okay, using the ideal information. And I find out that in reality it should come out with 3359 kilojoules per kilogram, which means that the temperature would be 445 degrees C, and the actual exiting entropy is 7.6, meaning that I do indeed have a positive entropy generation, which means that this is indeed a possible cycle. In our next video, we'll look at one of the other pieces of equipment.